Welcome to the video for Chapter 22. Today we're going to talk about what happens when there are more than one boundary that the electromagnetic waves need to interact with. If there's, and in particular we'll look at two boundaries. If there are these two boundaries, then we can draw what's called a bounce diagram and be able to analyze what is the strength of the reflected waves and the transmitted waves. We can also calculate the total reflection and the total transmission of those waves, and that will actually turn out to be a very useful thing. We've got a lot of ground to cover today, so I'm gonna skip straight to the historical perspective. Today's historical perspective is about Guillermo González Camarena. He was a Mexican electrical engineer who invented a method for transmitting color television efficiently. He did that when he was just 23 years old. And his invention was also used on the Voyager 1 space probe, and that was really the first opportunity to return high-quality images of Jupiter and its moons. So it's pretty exciting that we're now up to things that were really invented in the 20th century, in the 1900s, and in particular that we're able to have, we can say, electrical engineer rather than physicist. So let's talk a little bit about these bounce diagrams. What happens when an electromagnetic wave hits a boundary between two different materials and then a second boundary between two different materials? So let's look at this picture right here. I've got two boundaries between three regions. So region 1, region 2, and region 3. And I've drawn region 1 and region 3 with the same colors here for a reason. Ultimately, we'll probably think of this as a sandwich where epsilon R1 is equal to epsilon R3. But for right now, we're going to go ahead and leave it as general as we can. We actually have to allow for the reflection and transmission coefficients at each boundary, but we also have to consider in both directions. So if we're going from region 1 into region 2, then we'll have the reflection and transmission coefficients with the plus signs because the wave is moving toward the right. But if we're going from region 2 into region 1, then those will be the reflection and transmission coefficients with the negative sign because the wave is moving toward the left. Similarly, we'll also have a gamma 2 plus and a T2 plus. We'll also have a gamma 2 minus and a T2 minus. So we need to think about what's going to happen as a wave is coming in. And one thing that I can see, and I'll begin to sketch this as I'll see a bounce diagram, as a wave is coming in, part of it is going to be reflected and part of it is going to be transmitted. And the wave that gets transmitted is, of course, going to hit the second boundary. Part of that wave is going to get reflected and part of that wave is going to get transmitted. And that wave is going to hit the first boundary from the opposite side. Part of that will be transmitted and part of that will be reflected. And you can see the pattern here that we're going to have the wave, part of it is transmitted and part of it is reflected each step. So we need to think about each one of those steps, but then also we have to think about what happens to the overall wave. What is the overall result of all of those bouncing waves going back and forth? Well, we can calculate the reflection and transmission coefficients. We saw how to do that in Chapter 21. So we have gamma 1 plus, T1 plus, gamma 1 minus, and T1 minus. And you'll remember, if you want to check your answers, we saw that at each step, T is equal to 1 plus gamma. So we can check that we've actually done the calculations correctly. You'll also notice here, and I won't use this for a while, but the relationship between gamma 1 plus and gamma 1 minus is that they're negatives of each other. So gamma 1 plus is equal to negative gamma 1 minus, and that's simply because these two terms in the numerator are reversed. And since there's a negative sign, that yields a negative sign when we reverse them. We can also calculate the wave number in each of the three regions. And you'll remember that the wave number increases as epsilon r increases. So we've got k sub 0, which is the wave number of free space, multiplied by the square root of epsilon r in each region, or we could specify that as omega divided by c times the square root of epsilon r in each region. That won't be as important as the transmission and reflection coefficients, but it will be important before the day is over. So here you can see a full sketch of the wave that I sort of sketched in the previous figure. This is drawn in part so you can see all of the interactions, but also so that we can understand the notation. Notice that every wave that's moving toward the right has a plus superscript. Every wave that's moving back toward the left has a negative superscript. Also notice that the two subscript numbers, the first one refers, let's go to the second one. The second subscript number refers to the region. So you'll see here that, for example, this number, the comma 1, is for region 1. Here the comma 2 means that this is in region 2, and then the comma 3 means that it's in region 3. So the second subscript references the region, but the first subscript references the generation. And I say generation because, of course, here you can see that we're going to have a first generation wave, but then as it progresses through and bounces twice, it bounces, let's see, it's transmitted and then it bounces and then it's transmitted. We get a second generation wave in the same region going in the same direction, and then we get a third generation wave and so forth. If we didn't have that generation number, it would be impossible to tell those three waves apart from each other. Similarly, here we have a positive moving wave in the first generation within region 2. Here's the second generation of that same wave. Here's the third generation of that same wave. These two waves are both moving in the negative direction, so it's a first generation and a second generation. There is, of course, additional waves. There are, of course, additional waves going back and forth, but we have to draw the line somewhere. We can't draw forever, so that's what this ... implies, is that there are, in fact, additional waves moving down as we go through the bounce diagram. In a problem or in an exam, you'd be asked to say, I would give you exactly how far to go down and how many waves to account for. Over here again, waves moving to the right, we have first generation, second generation, and third generation. So we have a superscript that tells the direction. We have two subscripts, one of which tells the generation and one of which tells the region. So between those three identifiers, we can identify every wave uniquely in this picture. So let's consider calculation of each one of those wave amplitudes. So I'm gonna calculate the gammas and the t's first. So I know that gamma sub 1 plus is equal to, from the region that I'm in, which is the square root of 1, minus the region that I'm going to, which is the square root of 4, divided by the sum, and that gives me negative 0.333. And I can do t sub 1 plus, that is equal to 2 times the square root of 1 divided by the square root of 1 plus the square root of 4, and that gives me plus 0.667. Just checking there, t is equal to 1 plus gamma, so I've done those calculations correctly, most likely. Gamma 1 minus is equal to the square root of 4 minus the square root of 1 divided by the square root of 4 plus the square root of 1, which it turns out is plus 0.333. As we saw earlier, these two numbers have to be related with a negative sign, and so we're getting that correct here. And then t sub 1 minus is equal to 2 times the square root of 4 divided by the square root of 4 plus the square root of 1, and that turns out to be plus 1.333, and those two numbers do in fact obey the t equals 1 plus gamma relationship. So we have a number of ways we can check these numbers. There's a relationship between these two numbers, there's a relationship between these two numbers, and there's a relationship between these two numbers, and we can just use those to check the results and make sure that we've done the calculations correctly. So we have all the reflection and transmission coefficients. Let's take these one at a time. I'm going to go ahead and do the middle region first because I think that sort of forms the backbone for the rest of the calculations. So I'm going to do E sub 1 comma 2 in the plus direction. So I'm doing this wave right here. And all I need to do is look at the picture, and I can see that is going to be T sub 1 plus. So it's the transmission coefficient at the first boundary moving in the positive direction multiplied by the incoming wave, which is E sub plus of 1 comma 1. Well, we were told that E sub plus of 1 comma 1 has an amplitude of 10 volts per meter, and so this is going to be 0.667 times 10 is 6.67 volts per meter. So we've completed this wave right here. Now I can do E sub 1 comma 2 in the minus direction. That is going to be gamma sub 2 in the positive direction. So the reflection coefficient at the second boundary when moving from the left multiplied by the thing that we just found, which was E sub 1 comma 2 in the plus direction. So gamma sub, oh, there were some gammas that I didn't calculate. Oh, darn. Okay, so I better squeeze those in here at the bottom. Gamma sub 2 plus is going to be the square root of 4 minus the square root of 1 divided by the square root of 4 plus the square root of 1, which it turns out is plus 0.333. And then just to save space, I'll say T2 in the plus direction is going to be 1 plus gamma 2 in the plus direction, which is 1.333. And in my notes, I actually did that calculation fully, and I did get that result, so I can confirm that that's correct. So gamma sub 2 plus is 0.333 times the number that we just calculated, 6.67, and that works out to be 2.22 volts per meter. And you can see that that has completed that calculation. And then E sub 2 comma 2 in the positive direction, that's going to be equal to gamma, let's see, that's going to be equal to gamma sub 1 in the negative direction. So I have a wave that is coming in the negative direction, and it hits the first boundary. So gamma sub 1 in the negative direction times the thing we just calculated, E sub 1 comma 2 in the negative direction. So gamma sub 1 in the negative direction is plus 0.333 times 2.22, which is 0.740 volts per meter. So we've now done all of the waves in the middle here, so we've completed all three of those calculations. Let's do the ones in the left region here. So E sub 1 comma 1 in the minus direction, that's the first reflected wave, that's going to be equal to gamma sub 1 plus times E sub 1 comma 1 in the plus direction. So it's the incoming wave multiplied by the reflection coefficient at the first boundary when we're moving in the positive direction. And that works out to be negative 0.333 times 10, which is negative 3.33 volts per meter. So now we've also completed this calculation. And then E sub 2 comma 1 in the negative direction, that's going to be equal to T sub 1 negative times E sub 1 comma 2 in the negative direction. So that is to say, this wave that is coming in here, whatever portion of it gets transmitted, so that's why it's T1 minus, because it's the transmission at the first boundary moving in the negative direction, multiplied by E sub 1, 2 moving in the negative direction. So T sub 1 minus was 1.333 times E sub 1, 2 minus was 2.22. And so when I multiply those together, I get 2.96 volts per meter. And then finally, so let's see, that takes care of this wave right here. So finally, I only need to worry about the third region. So E sub 1 comma 3 in the plus direction, that's going to be equal to E sub 1 comma 2 in the plus direction times T sub 2 plus. This sort of calculation is why the bounce diagram is so helpful, because I can see the only source of this wave is the one that is coming in, and so I already know the name of that wave, and then it's transmitted through that boundary moving toward the right. And so this is going to give me equal to 6.67 times 1.33 equals 8.88 volts per meter. And then finally, so I will erase that, and so that takes care of that. And then I've got E sub 2 comma 3 in the plus direction. That's equal to E sub 2 comma 2 in the plus direction times T sub 2 in the plus direction, which is equal to 0.740 times 1.33 gives me 0.986 volts per meter. So we've calculated the strength of each of those 1, 2, 3, 4, 5, 6, 7 waves. And we could, of course, continue. We could keep going. We don't need to do that. But you can see the value of the bounce diagram and how the bounce diagram made it pretty easy to visually figure out what two things needed to be multiplied together for each of these calculations. You can also see that that's a bit of a pain in the neck, and you don't really want to have to do a lot of that. I could imagine doing this with a computer algorithm or even a spreadsheet, but what I'd really like to know is how much of the total wave gets reflected and how much of the total wave gets sent out. I know that in this middle region here, I know that the waves are going to bounce back and forth. They're going to bing, 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 bing. But as they do that, they're going to be decreasing in amplitude. So I also know that the waves that are outside the region are also going to be decreasing in amplitude. But I want to know how they interact with each other, and I want to know how much of the total wave gets transmitted and how much of the total wave gets reflected. I could think of this as a thin film, and I have a wave that's coming in, and yes, there's some stuff that happens in the middle here, but ultimately part of it gets transmitted and part of it gets reflected. And I want to figure out what is that total transmission and total reflection, and that's the next thing we can do. So we want to think about the total reflected wave. Well, the total reflected wave is going to be the sum of all the waves in region 1. Let's go back up here and see the sum of all the reflected waves. Well, here's part of the reflected wave, and here's part of the reflected wave, and if we had continued on, we would have had more. You can see here that all I've done is to sort of show those waves. And again, you have to draw the line somewhere. I'm going to show the first 4 of them because that's going to allow us to see the pattern, which will allow us to find a closed form solution. So I'm going to go a little bit quickly through this derivation because there's a lot of ground to cover, but I think that you'll find that the ultimate result is pretty desirable. So the overall reflected wave is going to be this E sub 1, 1 in the negative direction, which we can say, well, that's going to be E sub I, that's the incident wave multiplied by the reflection coefficient, and for the moment, don't worry about this exponent. But if we wanted to know what is the second wave, so the second portion of that means you're going to have the incident wave, and it first of all has to be transmitted through the first barrier, and then it's going to bounce off the second barrier, and then it's going to transmit in the opposite direction through the first barrier again. Let's scroll back up to that earlier picture and see what that means. It means that we're going to have a wave that's coming in, and let me erase these other marks on here. And what we're looking for is we're looking to calculate this wave right here. The only way that wave happens is you have an incoming wave that gets transmitted, then reflected, then transmitted. So that's the path that we're following here. So I have transmitted, reflected, and then transmitted. But notice that in the middle of that sandwich there, so this distance here is d2. that this wave has followed a path that went d2 this direction, then it went d2 back that direction. So the total path that it has followed is 2d2. Well, that total path of 2d2 is going to introduce a phase difference of e to the j 2 k2 d2. So remember that it's e to the j kz. Well, in the middle region, k is equal to k2, and the distance is equal to 2d2. So what we find here is that this phase difference is going to mean that, it's sort of like, you went to college, some of your friends from high school stayed home. Well, as you went out to college and came back, you changed. And so when you come back, maybe it's not the same as it was with your friends who stayed home. And in the same way, there's going to be a wave that bounces here, and then there's going to be a wave that follows this path, goes out, and then comes back, and then it's here. These two waves are not the same because the second wave has introduced a phase shift. It could be that phase shift is going to be positive. It's going to have positive reinforcement of the first wave, or it could mean that they're 180 degrees out of phase, and then that's going to lead to an interference. We'll refer to this as positive interference or negative interference. But you can see that if the wave went 2d2, then you're going to get this phase difference, this one right here. If it went 4d2, so if it went out and back and then out and back again, sort of like getting a master's degree, then you have twice as much phase difference, and then out and back again. This one got its PhD. That's e to the j 6 k2d2. You can begin to see the pattern here that, for example, in order to get this wave right here, it has to transmit, then reflect on the first barrier, then reflect on the second barrier, then transmit through the first barrier. And then to get the last one that goes 6, you have to transmit, then reflect, transmit. So this is a full representation of the first 4 terms of the reflected wave. Now we're going to call the total reflection coefficient gamma to be the ratio of all of that reflected wave divided by the incident wave. So that just means that each one of these terms contained an E sub I, I can cancel those e sub i's out. And that's really the only change that happened here. I guess I did take this out because really that didn't really make any difference. I just wanted you to see that in that case there is no phase shift because it hasn't gone anywhere. It's just bounced off the first barrier. So this is the equation 22.10 is the first is the representation of gamma. It's our first shot at gamma, but we can do a lot better than that. As I mentioned to you earlier, gamma in the negative direction is equal to negative gamma in the positive direction. And we also know that t in the positive direction is 1 plus gamma in the positive direction. And then if we combine those two together, we can find that t in the negative direction is 1 minus gamma in the positive direction. So up here, everything that's not a gamma in the positive direction is going to end up being replaced. Everything that's not, gamma in a positive direction is going to end up being replaced by gamma in the positive direction. Let's see if I missed anything else. So all of those. So what I can do is I can substitute equations 22.11, 12, and 13 into 22.10, and I end up with 22.14. And then I'm going to simplify that equation. For example, here you can see I have a 1 plus gamma 1 plus and a 1 minus gamma 1 plus. When I multiply those together, it's the perfect squares. So I get 1 minus gamma 1 squared. Well, now I'm going to make another assumption. I'm going to assume that the material in region 1 and the material in region 3 are identical. And I mentioned here earlier that I was eventually going to make that assumption. So region 2 is a thin film surrounded on both sides by the same material. And so we find then that epsilon R1 equals epsilon R3, and that means that gamma 2 in the positive direction is equal to negative gamma 1 in the positive direction. And you can go back and look at the original definitions of gamma and see that equation 22.17 is correct. So that means that if I go back up to this equation 22.15, which we had earlier, now I'm going to replace all of the gamma 2's with the corresponding relationship of gamma 1. And I don't need to worry about the pluses and minuses anymore because they're all plus. So I get down to just the gammas. You can see there's a lot of occurrences here of, say, 1, 2, 3 negative gamma 1s, and here there's 1, 2, 3, 4, 5 negative gamma 1s. So I can simplify things a little bit here. You can see that this it's always an odd number of negative gamma 1s. So there's 1, and then 3, and then 5, and so here is 1. I guess I shouldn't write that. That looks like a 0. So it's gamma 1 to the 1 power, gamma 1 to the 3rd power, and gamma 1 to the 5th power. And the equation 22.19 is beginning to get a little bit simpler. Factoring this, I'm going to factor, so I bring down the gamma 1, so the gamma 1 there becomes the gamma 1 here, and I'm going to factor essentially this entire term out of all of the remaining terms. So it's gamma 1 to the 1st power times 1 minus gamma 1 squared times e to the j 2 k2 d2. And so I end up with an expression that looks like the rest of this right here. I'm going to define a temporary variable, which is gamma 1 squared e to the j k2 d2. And that allows me to rewrite the thing that's in the brackets as 1 plus x squared plus x cubed and so forth. But mathematicians have shown us that that is just equal to 1 over 1 minus x. So I can then substitute that for 1 over 1 minus x. Everything else stays the same between equation 22.22 and 22.24. Now I'm going to resubstitute back in x. Probably a little bit more explicit than I need to be in this derivation, but I want to make sure that you see all the details and that I'm not pulling any fast ones on you here. So I've resubstituted in for x. I'm essentially now going to bring this right here up into the numerator here, and I'm going to factor a gamma out of the whole thing. So this gamma 1, I'm going to factor a gamma 1 out of the whole thing. This gamma 1 right here ultimately becomes the 1, and everything else becomes this quantity right here. Now I need to have a common denominator, so I'm going to multiply that 1 through by the thing that is the denominator of the second term. And now I do have a common denominator. And then here's the very interesting part. I can cancel, this is negative gamma 1 times the gamma 1 squared times the exponent, and this is a positive gamma 1 squared times the exponent. So those two are going to cancel each other. And then I end up with, this is really just 1, and this is minus 1 times this exponent. So 1 minus the exponent. and then the denominator remains unchanged. So there I have a final closed form expression to represent the total reflection coefficient. We covered a lot of ground to get there, but we don't have to do that again. Now we can just have this, which is our ultimate final answer for gamma, the total reflection coefficient. And then a similar derivation, which I'm omitting to save us both a lot of time here, will give us the transmission coefficient, the total transmission coefficient, given all of that other information. So notice that the reflection coefficient and the transmission coefficient will depend on gamma 1, it'll depend on K2, and it'll depend on D2. So we need to account for all of those quantities when we are solving for gamma and T. So let's calculate the total reflection coefficient and the total transmission coefficient for a thin layer with relative dielectric constant of 4 and a thickness of 2.5 centimeters surrounded by free space on both sides and a frequency of 10 gigahertz. Okay, so I can calculate K2 is going to be equal to omega over C times the square root of epsilon r. And that is going to be equal to 2 pi times 10 to the 9th divided by 3 times 10 to the 8th times the square root of 4. And that's equal to 418.8 meters to the minus 1. So that's K2. I can also calculate gamma 1, which is really gamma 1 plus. So this is the square root of 1 minus the square root of 4 divided by the square root of 1 plus the square root of 4. And this is minus 0.333. Then I can calculate the total reflection coefficient gamma. This is going to be equal to minus 0.333 times 1 minus e to the j 418.8 times 0.025 because it's 2.5 centimeters. And then that's divided by 1 minus negative 0.333 times just the e to the j 418.8 times 0.025. If you plug all of that into your handy complex capable calculator, you get minus 0.495 plus j 0.228. And if you convert that into polar form, you get 0.545 at an angle of 155.2 degrees. And so that's the total reflection coefficient, and it is a complex number because the complex number there represents the phase. So 54.5% of the strength is reflected, but it has a total phase shift of 155 degrees. So it includes both the amplitude and the angle. We can calculate the total transmission coefficient. This is going to be equal to 1 minus negative 0.333 squared, and that's going to be times e to the j 418.8 times 0.025, and then all of that is divided by 1 minus negative 0.333 squared times e to the j 418.8 times 0.025. And when we plug that into our calculator, we get negative 0.3516 minus j 0.7613, which is 0.8386 at an angle of negative 114.9 degrees. So is more of the wave transmitted or reflected? More is transmitted, but a substantial portion of it is reflected. You might say, well, that doesn't seem like, how is it that 54% of the wave is reflected and 84% of the wave is transmitted? This is the amplitude, and so we have to deal with the square of the amplitude to get the power. So what we're going to find, and there's another very important expression coming up, we'll find that the squares will add up to 1, but the individual components don't add up to 1. So we can actually perform a calculation, and I did this calculation in MATLAB, to see what happens to the reflection coefficient and the transmission coefficient at a variety of different frequencies. So this is, and I know that it's hard to read this, so I'm going to enlarge this. This is 1 gigahertz, 2 gigahertz, 3, 4, 5, 6, 7, 8, 9, and 10 gigahertz. And if you remember, the previous example that we just did was 10 gigahertz. So these two points that I've circled right here correspond to the numbers that we just calculated. And sure enough, those in fact are the numbers that we just calculated. But this graph then includes all of those numbers between 1 gigahertz and 10 gigahertz. I also just want to point out that this top line up here corresponds to a reflection coefficient or a transmission coefficient of 1. So you can see that at certain frequencies, 100% of the wave is getting transmitted. And that corresponds to places where 0% of the wave is being reflected. And so those are very interesting points, because that allows us to identify places where there is no reflection. And so, for example, if you wanted an anti-reflection coating, you would want to choose those points. And what we've done here is we've set the thickness and then we've determined the frequencies. But in reality, what you would do is you would know the frequency that you want to prevent reflection on, and then you would determine what thickness would prevent those reflections. We also, as I mentioned before, know that the magnitude of gamma squared plus the magnitude of t squared is always going to be equal to 1 at every frequency. That's very easy to see at, say, this frequency, where it's the square root of 0 squared plus, it's 0 squared plus 1 squared equals 1. But at every frequency, this is the case. And if you go back up to the example that we just did, and if you take 0.545 squared plus 0.8386 squared, you'll end up with 1. And I did double check that to make sure that it was correct. So that means that we're going to be able to pretty easily break down what fraction of the energy, what fraction of the power is transmitted. That would be the t squared, the amplitude of t squared, and what fraction or portion of the energy is reflected. That would be the magnitude of gamma squared. So what are two frequencies at which the system in figure 22.3 will yield 0 total reflection? Well, that's just a matter of looking at the graph and seeing where gamma is equal to 0. There are actually 3 of them on this graph, and you can probably infer from that, since they're at regular intervals, you can probably infer that that would continue. So we've got 3 gigahertz and 6 gigahertz. And since it only asked for 2, I'll just list those 2, but just between us, you'll know that 9 gigahertz would have also been an appropriate answer there. So that's what happens when there's a little sandwich, when there is a thin layer that has a different dielectric constant than all of the surrounding regions. Let's talk about another special case of reflection, and that is when you have a wave that is propagating through free space and it reflects off of, or it encounters, a perfect, and when I say perfect conductor, I mean like any sort of metal is going to be a very, very good conductor approaching a perfect conductor. So we'll go ahead and say a very good conductor, a piece of metal. What we find then is that it's going from a region in which the characteristic impedance is 377 ohms into a region in which the characteristic impedance is approaching 0. And I don't know if you remember this, you may not, but way back in chapter 20, 2 chapters ago, we saw that the limit of Z sub C, the characteristic impedance, as sigma goes to infinity, so this would be a very good or a perfect conductor, this is going to approach 0. So the characteristic impedance of a piece of metal is going to be equal to 0. So what we find then is we can calculate the reflection coefficient, and we had the equation 21.37. We've become accustomed to doing these calculations in terms of the relative dielectric constant, but here we can do it in terms of the characteristic impedance as well. We find that Z sub C2, which is the metal, is going to have a characteristic impedance of 0, so that's going to appear here and here. And then free space, which is region 1, that's going to have a characteristic impedance of 377 ohms. And the negative sign in the numerator means that that's going to end up being a negative 1. So 100% of the wave is going to be reflected, but it's also going to be inverted. We're going to find that the amplitude of the, I guess you should say the phase of the reflected wave is going to be out of phase with the incoming wave, or the incident wave, by 180 degrees. So the 180 degrees difference is going to come from that negative sign right there. Now that may not seem like it's a super interesting case. In fact, it might seem like it's the most boring case, but it turns out that it yields extraordinarily interesting and valuable results. So let's consider, first of all, we're going to have an incident wave which has an amplitude of C. The amplitude isn't really critical, but there is one interesting thing about the amplitude that we're going to see. We're going to say that it's moving in the positive direction, and that's where that negative kz is coming from. So according to equation 22.31, when this wave hits the metal boundary and begins to bounce back, we've introduced a negative sign here, which is going to correspond to the negative sign in gamma. And now, of course, it's moving to the left, and so that's why this is plus kz. Well, the total wave in the region of free space is going to be equal to the incident wave, so this is E sub I, plus the reflected wave, so this is E sub R. So we can add those two together, but the negative sign of E sub R becomes this negative sign right here. They're added together, but it becomes subtraction because of this negative sign right here. So we're going to factor out the amplitude, C, and the time dependence, e to the j omega t, out of both of those two terms. And then we're going to go back to essentially Euler's identity. It's not precisely Euler's identity. It is an identity that relates the sine function and complex exponentials. I just want to draw one thing to your attention here. Up here, the negative is first and the positive is second. And in this identity, it's the positive is first and the negative is second. So I just want to draw that to your attention, that this is going to introduce an extra negative sign here. So the e to the j theta minus e to the negative j theta is equal to 2j times sine of theta. We could also say e to the negative j theta minus e to the j theta is equal to negative 2j sine of theta. And that's what we're going to plug right back up into equation 22.36, because there we have e to the negative j something minus e to the positive j something. So that's where the sign of kz is going to come from. So we have negative 2j. This negative 2j comes from this negative 2j. And it was, let's see what it was. It was e to the j kz. So theta is equal to kz. So theta is equal to kz in this case. And that's why this becomes sine of kz. Well, when we, let's see, e to the j omega t, that's going to be equal to the cosine of omega t plus j times the sine of omega t, and that, I believe, is Euler's identity. But we have it's multiplied by this negative 2j. Well, j times j is going to give a negative 1, and so ultimately what happens is this is going to become, the imaginary is going to switch from the sine to the cosine because we multiplied by j, and then the negative sign that is j squared is going to cancel with this negative sign right here, and we end up with positive 2 times c, which is the amplitude of the original wave, times sine of omega t times sine of kz. Now this then, equation 22.39, probably looks like 1,000 other equations that you've seen in this book so far. But I want to point out that there's a dividing line here. And everything that is t dependent is in one sine wave, and everything that is z dependent is in the other sine wave. What we're accustomed to is that there'd be like an omega t plus or minus kz. And they're sort of merged together, and those waves move to the left and they move to the right. Those are known as traveling waves. But this wave in 22.39 doesn't travel. It actually marches in place. If you're in marching band, this is like where you're marching in place. And that's why it's known as a standing wave, because the standing wave doesn't move. It just stays in one place, and it grows and shrinks, and it grows and shrinks, but it never moves. And I've tried to represent this. The best way to understand a standing wave is to see sort of an animation of it, but I've tried to represent this in a figure here. We're going to say that at t0, it's going to be flat, and then it's going to grow at t1. Notice that at t1, that we actually have a single sine wave here, and so it is sort of, I'm trying to follow the purple path here, and so that's what it looks like at t1. At t2, it's going to grow in amplitude. At t3, it'll grow and sort of approach its peak amplitude, which is going to be 2. Notice that this over here is 2. It's not equal to 1 because this 2 right here means that the amplitude of the total wave is double the amplitude of the incident wave. So after it reaches t3, now, and notice that, oh gosh, this is hard. As I'm coming up to t3 here, I'm going to erase a few more things. t3 then is this orange path right here. And what I'm going to do is I'm going to say, instead of thinking about t3 being up here, now I want you to think of t3 as being down here. And then as time continues to t4 and t5 and t6, that wave is going to shrink in amplitude. Then as time continues even further, it's going to increase in amplitude, but it's going to increase in amplitude in the opposite direction. So we've introduced a 180-degree phase shift, or a negative sign, and that negative sign means that no longer are we peaking here, but now we're peaking here. And so that standing wave has flipped direction. It has flipped by 180 degrees, and no longer is it peaking in the column where it was. Now it's going to peak in the next column. And then, of course, at T10, 11, and 12, we're going to go back down to 0, and then the cycle is going to repeat again. So again, probably hard to understand this from a single figure, but what I want you to see is that as the incident wave is coming in from the left and it bounces off the metal, the reflected wave and the incident wave will interact with each other in such a way that the waves are going to stay in place. The nodes, which are the places where there are 0 voltage, and the antinodes, which end up being the maximum and minimum, those are going to stay fixed. These nodes right here, those are not going to change with time. The only thing that changes with time is the height of the wave that occurs between the nodes. That's really the most important thing to realize about the standing wave. So what is the frequency of that standing wave? Let's go back up here and look at this. Remember that, let's imagine I'm going to focus on this orange wave right here. So remember that this orange wave is doing this, and it comes back up here, and it hits right there. And that is why I've written this and shown that lambda is actually the distance between, it's 2 nodes worth of direction. Because here's a node right here, but then here's a node, and here's a node, and the distance between, I guess, 2 nodes worth of distance is equal to lambda. And again, I know that this is really hard to read, but that is 0.15 meters. So what we can do is we can say lambda, that's a horrible lambda. So lambda is equal to 0.15 meters, and k is equal to 2 pi over lambda. That's equal to 41.89 meters to the minus 1, or radians per meter. We know that k is equal to omega divided by the velocity, and in free space, that's omega divided by c. So we can say omega is equal to k times c, which is going to be 41.89 times 3 times 10 to the 8th, and that works out to be 1.26 times 10 to the 10th radians per second. And f is omega over 2 pi, which is 2 times 10 to the 9th hertz, which is 2 gigahertz. So just by knowing where the nodes are located, just by knowing how far it is to the nodes, we can identify what is the frequency of this wave, because we know that it's free space. And so therefore we know the speed of light in free space. Okay, now let's consider a 5 gigahertz electromagnetic wave incident on a perfect conductor at z equals 0. And so it's basically the same thing we've just been talking about. The amplitude of the incident wave is 1 volt per meter. It's polarized in the positive y direction. Determine full expressions for the incident and reflected electrical and magnetic fields associated with this wave. So we've got incident, we've got reflected, we've got electrical and magnetic. So there's incident electrical, reflected electrical, incident magnetic, and reflected magnetic. We have to find all 4 of those. Well, first of all, let's calculate omega. Omega is equal to 2 pi f, which, I'll skip plugging the numbers in there, but it's 3.14 times 10 to the 10th radians per second. And we can calculate k is equal to omega divided by c. Again, it's in free space. So that turns out to be 104.7 meters to the minus 1. I can now immediately write the incident electrical wave. So the incident electrical wave, which is a function of z and t, of z comma t, is equal to, we were told that the amplitude was 1, so it's 1 times cosine of omega, 3.14 times 10 to the 10th t, minus k, which is 104.7 times z, and that's in the a sub y direction, because we were told it's polarized in the positive y direction, and it is in units of volts per meter. So there's 1/4 of the problem already solved. Now, we know that that a sub k, let me make a note up here, a sub k we know that the direction of motion is in the positive z direction. Because we know that it's incident on a perfect conductor at z equals 0, so it must be approaching it from the left if it's at z equals 0. We can go ahead and draw the axes here. I'm gonna draw them up here in the space above. So I know that I have a sub x in this direction. If I have a sub y in this direction, then that'll yield a sub z in this direction. And you have to think about x crossed y gives z, so you put your fingers in the direction of a sub x, curl them in the direction of a sub y, and then your thumb sticks in the direction of a sub z. Well, I know that this is also equal to a sub k, and I know that this is also equal to a sub e. So a sub e is equal to a sub y, and a sub k is equal to a sub z. The question is, what is a sub h? So a sub h is always going to be equal to a sub k, let me try this, a sub k crossed with a sub e, which in this case is going to be a sub z crossed with a sub y. If you put your thumb in the direction, if you put your fingers in the direction of a sub z, curl them in the direction of a sub e, then your thumb is going to point in the direction of negative a sub x. So this is a sub h. So this is equal to negative a sub x. So we can actually now write the incident magnetic wave, h sub I of z comma t. We know that the amplitude is going to be controlled by the characteristic impedance of free space, which is 1 over 377. So it's the amplitude of E divided by z sub 0. And that's going to be multiplied by the exact same cosine. It's always the exact same cosine. 3.14 times 10 to the 10th t minus 104.7 z. And we know that that's times negative a sub x. And it's in units of amps per meter. So we can write this as, let's see here, what can I get? I get negative 2.65 cosine of 3.14 times 10 to the 10th t minus 104.7 z, and that's in the direction of a sub x, and the units are milliamps per meter. So that's the incident magnetic wave. The reflected electrical wave is actually pretty easy to calculate. E sub r of z comma t is just going to pick up a negative sign, so it's negative 1 cosine of, you know what, yeah, I'll write it out fully because it says to do it fully. 3.14 times 10 to the 10th t minus 104.7 z, and that's still in the a sub y direction but with a minus sign, and that's in units of volts per meter. I think that is probably sufficient for the reflected electrical wave. And now let's think about what happens in the reflected case. So again, I'm going to draw my electrical, my sort of unit vectors. So here's a sub x, a sub y, and a sub z. Well, now I know that the direction of motion is actually going to be in the negative a sub z direction. So a sub k is now this direction. And I know that my electric field also has reverse direction, so here's a sub e. And so what is the magnetic field? The magnetic field is going to be, let's see, I'm going to point my thumb in the direction of a sub k. I'm going to curl it. Oh, you know what? I got this wrong. This is not the direction of a sub, so this is a sub e. And so when I put my thumb in the direction of a sub k and I curl it in the direction of a sub e, I find that the magnetic field is still in the same direction. It's still negative a sub h. It's still negative a sub x. So h sub r of z comma t is equal to negative 1 over 377 cosine of 3.14 times 10 to the 10th t minus 104.7 z. And it's going to be in the negative a sub x direction. I've already accounted for the negative sign there, so I'll just say a sub x, and that's in units of amps per meter. Or I can say h sub r of z comma t is equal to negative 2.65 cosine of 3.14 times 10 to the 10th T minus 104.7 Z A sub X milliamps per meter. And we're able to identify the electric and magnetic field in the incident and reflected directions, and to give a full specification of them. Anything that we would want to know, we can find from there. Just remember that we always find the magnitude of the magnitude of the magnetic field is equal to the magnitude of the electric field divided by Z sub C, which for free space is 377 ohms, and the direction of the magnetic field is equal to the direction of motion of travel crossed with the direction of the electric field. If you remember these two facts, you can always find the magnetic field given the electric field and the direction of travel. Okay, so and here's just sort of a one-off problem. A wave of unknown frequency is incident on a perfect conductor is equals 0. You measure nodes every 10 centimeters away from the conductor. What is the frequency of the signal? So remember that the distance of the nodes, so 0.1 meter, that's the distance between two nodes, but the distance between two nodes is not lambda, it's lambda divided by 2. Let's scroll back up here and see that this distance between two nodes, that's lambda divided by 2, because it takes two nodes worth of distance to get a full wavelength lambda. So we know that 0.1 meters is equal to lambda over 2, therefore lambda is equal to 0.2 meters. We can calculate k is 2 pi over lambda, which is 31.4 meters to the minus 1. Omega is equal to k times c, which is 9.42 times 10 to the 9th radians per second. And f is equal to omega over 2 pi, which is 1.5 gigahertz. So just knowing how far the spacing is between nodes will allow you to determine the frequency of the wave that's being transmitted. And then the last topic for today is what happens if you have two pieces of metal parallel to each other and close enough that they'll interact with each other. Well, what we're going to find is that a wave is going to set itself up in that space. You know, we have, let's say that this distance here, we'll call this d, and that wave that sets itself up is going to have a wavelength. It's going to have a wavelength such that there's a half a wavelength within that region d. So we can say d is equal to lambda over 2. We can then multiply both sides by 2. So 2d is equal to lambda. And we know that lambda is equal to 2 pi divided by k. So 2 pi over k is equal to 2d. Cancel out the 2's. Solve for k. So we find that k is equal to pi over d. But we also know that k is equal to omega divided by v. So omega divided by v is equal to pi over d. We can then solve that for omega, pi times v over d. But we also know that v is equal to 1 over the square root of epsilon 0, epsilon r, mu sub 0, neglecting the mu sub r because we're not talking about moving through a ferromagnetic material. And so we can substitute that in, and we end up with equation 22.4. We'll now put a little subscript r on this to say that this is the resonant frequency. This is the frequency of the wave that will be created in between those two plates. So you move two pieces of metal very close together, and it turns out that a frequency is created in between them. If we have such a region between two nearly perfect conductors, that's known as a Fabry-Perot cavity. So Fabry-Perot cavity, we can determine what is the resonant frequency of any Fabry-Perot cavity. So let's consider everything that we know in this equation. Let's imagine that we know the resonant frequency. Let's imagine that we know that the distance between the two plates. The only thing that's unknown here then is the relative dielectric constant. So we can use this as a very precise way of identifying the relative dielectric constant in between the two plates. You know, we've got a plate, and in between there is something, and that something has a relative dielectric constant epsilon r. So we can calculate that relative dielectric constant extraordinarily precisely because we can identify the frequency extraordinarily precisely. So let's figure out what is epsilon r. So I know that omega r is equal to 2 pi times f sub r, and that's equal to, just taking from the equation up above, that's equal to pi divided by d times the square root of epsilon 0, epsilon r, mu sub 0. Pi's are going to cancel, and I'll move the 2 over to the other side. So f is equal to we're going to have a 2d in the denominator, but I'm going to take that square root of epsilon 0 mu sub 0 in the denominator. I'm going to make that into a c up in the numerator, and then I still have an epsilon r square root in the denominator. So if I want to calculate epsilon r is going to be c divided by 2df, the quantity squared. Well, I know c, I know d, and I know f, so I can calculate epsilon r. So epsilon r is equal to 3 times 10 to the 8th divided by 2, that's just the number 2, times the size of the cavity, which in this case is a half a meter, and then the frequency f is 250 times 10 to the 6th. And that quantity is going to be squared, and this gives me 1.44 is the relative dielectric constant. And however precisely we can measure the resonant frequency, that's the same precision with which we can measure the relative dielectric constant. But what happens if the material inside changes? So we can use it to detect very small changes in the total dielectric constant in the space between the conductors. Let's consider we have a resonant frequency change, which is going to be the original resonant frequency minus the new resonant frequency. We're going to substitute what we know for the resonant frequencies. And so this is omega r1, and this is omega r2, and the only thing that is different is the epsilon r in between those two equations. So we can then say, what happens if we take that change and we divide it by the original omega r1? Well, a lot of things are going to cancel. The pi's are going to cancel, the d's are going to cancel, the epsilon zeros are going to cancel, the mu sub zeros are going to cancel, and all we're left with is some relationship in epsilon r1 and epsilon r2. If we're then going to assume that epsilon r1 is equal to 1, so this is free space or an empty cavity, therefore the original omega r1 was the frequency of the empty cavity, then equation 22.47 reduces down to equation 22.48. Remember that the epsilon r1 is going to go to 1, and this is going to go to 1, and this is in the denominator of the numerator, so it just becomes in the denominator. So if we know the percent change in the resonant frequency, we can use that to calculate how much epsilon r was just introduced into the region. So we have an empty Fabry-Pro cavity which has a width of 0.1 meters, so 10 centimeters, that's about 4 inches. So I just want you to have in mind that this is about 4 inches. If imperial units are helpful to you, it helps me to be able to visualize, okay, that's about that's the size of my hand or something like that. When a sheet of paper is inserted into the cavity, we can detect that sheet of paper. The resonant frequency decreases by 0.1%. If paper has a relative dielectric constant of 3, then what is the thickness of this sheet of paper? So we're going to insert, and I've shown it in red here, and so that red thickness T, how much of that is going to be the thickness of the sheet of paper? So we know that delta omega r divided by omega r1 that's the percent change, and that's going to be 0.001, because 0.1% is 0.001. And we know that that is equal to, 1 minus 1 over the square root of epsilon r2. Epsilon r1 was just 1, because that's what it was before we inserted the piece of paper into it. So we can then calculate from this 1 over the square root of epsilon r2 is equal to 0.999, and therefore epsilon r2 is equal to 1.002. So it's not very much change in the relative dielectric constant, but then again, it wasn't very much change in the frequency. So we know epsilon r2, and I'm not going to derive this equation, but I think you would believe me that if we have a portion of the space in between the two pieces of metal that is air, and a portion that is the piece of paper, that the total relative dielectric constant of that combination is going to be the weighted average of the two dielectric constants. So epsilon r2 is equal to whatever the amount d minus t divided by d times epsilon r of air. And so that's d minus t is everything that is not the piece of paper. And so d minus t divided by d, this is the percent of air multiplied by the epsilon r of air, plus t divided by d, that's the percent that is paper, multiplied by epsilon r of paper. And we know that that combination is 1.002 because we just found that up above. Well, we know D. D is 1/10 of a meter. So 0.1 minus T divided by 0.1 plus T divided by 0.1 equals 1.002. If we multiply both sides by 0.1, we get 0.1, oh, hold on, I forgot an epsilon r of paper. So this is just equal to 1. This is equal to 3. So it's T times 3. So 0.1 minus T plus 3T is equal to 0.1002. This left-hand side, I'm going to reduce that down to just 2t. So 2t, I'm going to subtract 0.1 from both sides, is equal to 0.0002. And t is equal to 0.0001 meters, which is 0.1 millimeters. And that's about right for a sheet of paper. 10 sheets of paper to a millimeter. Is 10 sheets of paper about the thickness of a dime? It's probably in the right ballpark. It's remarkable to me, though, that if you think about the fact that I have this region, which is 4 inches wide, I can detect when a single sheet of paper is inserted into that simply because it changes the resonant frequency of that region. And so that's it. That's all of the new material for today. We saw that we can generate a bounce diagram. We can calculate the total reflection coefficient, the total transmission coefficient. We saw that their squares of the amplitudes have to add up to 1 because that'll be conservation of energy. We saw that the standing waves break the time dependence and the spatial dependence into 2 parts, and that these have nodes that don't move and antinodes that don't move, but they do increase and decrease in time. And we find that those nodes are going to be 1/2 wavelength apart. So whatever is going on here, those nodes, this distance here is going to be lambda divided by 2. 2 nearby conductors will create a resonant standing wave between them that has a resonant frequency that can be calculated according to that equation. And if you have an empty cavity such as that one with a resonant frequency of omega r1, and you insert a dielectric material between the plates, and that results in a change in the resonant frequency, then the dielectric constant between the plates can be calculated according to this equation.